Okay, welcome everyone to the 20th IDS Scholar Seminar Series. Okay, today is our honor to have Professor Xihui Liu here, who is jointly hosted by the Institute of Data Science and the EEE department. Okay, let me briefly introduce Professor Liu. Professor Liu received her PhD from CHK and also the postdoc fellow from UC Berkeley. And her research interests cover computer vision, deep learning, and AI, with emphasis on generative AI, multimodal AI. She was awarded the Stanford World's Top 2% Scientist 2025 WAIC World AI Conference, Rising Stars Award 2022, Rising Stars in the UC Berkeley, right, ECS 2021, and Adobe Research Fellowship 2020. So let's welcome Professor Liu.
Okay, thank you. Okay, thank Professor Luo for the introduction. And today I'm very happy to share the multimodal and the interactive video generation towards world models. So in this talk, we will share a series of our group's work on generative models and also forward-looking towards the future world models. Yeah, so I think I don't need to mention a lot about how much progress the diffusion models have been made in the recent years. So diffusion models have achieved very great performance on image generation and also video generation. But beyond this success in text-to-image or text-to-video models, we are also asking, as more and more techniques has transferred from academic to the industry, so what's the next for visual generation? Are there further areas that hasn't been explored in the past that are very important? So I take Genie 3 as an example in this work. This work was released by Google in August this year. And in this work, it shows the some capabilities beyond the traditional text-to-video generation, which is called word models. So as shown in this video, users can not only use a text prompt to generate videos, but also they can interact with the generated videos in real time. Like we can interact with the videos with keyboard or mouse, and also with text prompt and other action space and other actions. So we see very strong scene consistency in this type of models. For example, if we brush this wall and this camera moves to the right and then to the left, and we still see the same scene. So this shows that the Genie 3 model has strong scene consistency. So how do we achieve such capabilities for the future world models? So we propose this blueprint for the future world models. Like on the left, we show the real world, the users, players, designers, agents, and also robots in the real world. So they are all agents interacting with our world models. So the world model constitutes a virtual world on the right. And in this world model is built upon the video generation model. And if we look at the interface, the interaction interface, we see that the users or agents can pass the actions, the instructions, and also visual input into the generative model. And this generative model generates video as the virtual world to the real world. So which capabilities are required for this type of world model? So we think the first very important capabilities are streaming generation, because we want to interact with the video for a long time. So we need the generation we need a streaming generation. And also we need the generation to be real time, because we need interactive, so we need real time generation. And the last thing is multimodal. So multimodal for the first perspective, because our interface is multimodal, so the user can pass multimodal prompts or multimodal actions to this world model. And on the other hand, we require a lot of reasoning capabilities for the world model. And these reasoning capabilities also come from the language model or multimodal model. So this is why we think multimodal is also a very important perspective. And besides the basic generation model, there are also some higher level capabilities that we want to inject to this generation model. So the first one is control. So since we want the user to interact with the video generation model by action control and other type of control, so we need very strong controllability for this model. And also, since we are considering the dynamic video, so we want the generated video to follow the real world physical law. And additionally, memory is very important, just like what we see in Genie 3. So we categorize the memory into two types. One type is static memory, which means that it mostly memorizes the scene, the static scene. So if the user moves around the scene itself keeps consistent. And another one is the dynamic memory, which means that the scene also involves with the user interactions. For example, if we push the door will open, and the next time we see this door, if without other user interactions, this door will keep open. So we need the model to be able to have this dynamic memory and also have the ability to update the memory. And the last one is a more high-level capability, which is we call intelligence. So in intelligence, we include not only the reasoning capabilities that are explored in language models, but also the self-evolution capabilities, which means that the model should be able to self-evolve to improve itself by interacting with users. Yeah, so in this talk, I will introduce a series of our group's work addressing some perspectives of this figure. So we will first introduce how to achieve generalizable interactive control for streaming video generation. And also we explore how to keep the consistent scene with a memory mechanism for very long video generation. And the third one is multimodality, because we said that we need the interface to be multimodal, and also we need reasoning capabilities, which often arises from multimodal models. So multimodal is also one important perspective, and the reasoning capabilities rise from the multimodal models. And finally, we will talk a little bit about the architecture. So nowadays, the most mainstream architecture for generative model is still the diffusion model. But we are also interested in other paradigms for visual generative models, like autoregressive models. So our group has a series of work exploring the potential of autoregressive models. And we think that autoregressive models, because it can naturally generate videos streamingly, and also it is easy to inject action signals. It is easy to inject combine with language models to achieve native multimodal models. So based on these reasons, we believe autoregressive models will be a promising approach to these word models in the future. Yeah, so let's start with the first one. About the generalizable interactive control and the streaming video generation. So last year, we see some preliminary works exploring how to use video generation model to fit a video game like this. But we observed that for these works in the last year, they are merely replicating existing games and cannot achieve new game generation and generalizable generation. So we aim to generate an entirely new games and control the characters in the new scenes. And we found that the key to address this problem is achieving a generalizable control in the open domain scenarios. So how to achieve this? In this work called Game Factory, we try to use the generative prior from a pre-trained video generation model, and alongside with a small-scale data set collected from Minecraft videos to achieve generalizable interactive videos. So from these two factors, the pre-trained video generation models provides us the generative prior for generalized scenes. And the Minecraft videos provides us the information about action control. So we need to combine these two information in a single model. And the way we do it is that, so the key to this approach is how to disentangle the style in the generalized video generation model and the action control from the Minecraft video. Because if we simply use the Minecraft video and train the action control collected by Minecraft video on the video generation model, the model will easily overfit to the scenarios of Minecraft, which is undesirable because we want the video generation to be generalizable, not just overfitting to the Minecraft videos. So we design a phased strategy to achieve this. So in phase 0, we see that we adapt a pre-trained video generation model. And in phase 1, we are using a LoRa to feed the style information or domain information from the Minecraft videos. And we keep the parameters of the initial video generation model fixed. And then in phase 2, we keep the LoRa freezed and the initial parameters freezed. And then we specifically use Minecraft video with action control to train the action control module. So the reason why we disentangle the style LoRa and the action control is to prevent the model from overfitting to the Minecraft style while when training the action control on Minecraft. And finally, we can remove the Minecraft style LoRa and use the original parameters together with the action control to generate open domain controllable videos. We also investigated how to inject the discrete control signals from keyboard and continuous control signals from the mouse into the diffusion video generation model. And another thing is the streaming generation. So in order to achieve streaming generation, we enable the model to learn to condition on the preceding frames to generate the subsequent frames. And with these designs, we show that our model is able to learn the action control from Minecraft, but to generate new videos beyond the Minecraft style in the open domain. So these are the demos of our generated videos. And this WASD space shift and control denotes the user interaction signals. So we see that we can inject any interaction signals into the video generation model. But there's a limitation of this work that we found that if we just keep going forward, it doesn't matter. But if we go forward and then go backward to the original location, or if we turn right and then turn left, we see that the model is not able to keep a consistent scene. Like in this demo, when we move right and then move to the left, in principle, it should be able to generate the original scene that it has generated in the previous frames. But actually, this model just generates a new scene, a randomly new scene. So this inspires us that memory mechanism is lacking in current video generation models. And this inspired our next work, the context as memory. So this is how current video generation models use the previous frames as context. So we just keep the nearest history context and use it as condition to generate the new green frames. But this is not ideal because ideally, the model should be able to condition all of the history information so that it wouldn't forget the previously generated information. But conditioning out of the yellow frames will cause a lot of computational inefficiency problems, and this is very hard to implement on the current models and current hardware. So motivated by this, we are inspired to propose a strategy to retrieve the keyframes or the key memories from all of the previously generated frames. And so assume if we have a good memory retrieval module that can retrieve the keyframes from all of the history frames, and these keyframes can act as the condition when we generate the future frames. So in this way, we should be able to leverage all of the history context information to generate new frames. But the problem is, how do we implement this memory retrieval module? How do we retrieve useful context from all of the history frames? So we examine the overlap between the field of view of all of the context frames and the predictive frames. So for example, in this video, we assume that we are going to generate this pink frame, this red frame, and then we examine the field of view of all of the other frames with this particular frame. And if they have a very high overlap in the field of view, then we can see that the corresponding context frame is very important for generating this new frame. So based on this strategy, we can retrieve that these yellow frames are most important for generating this new frame, and the gray and the black frames are less important. So in this way, we can extract. Oh, sorry. So in this way, we can extract the useful memories from the history frames and use it as condition to generate the new frames. And another thing that I want to mention is that we think the memory retrieval module in this work is just a very preliminary design, and there's still a lot of space to explore, like how do we extract it, how do we extract the useful memory from the context information, and how to update the memory. If we are treating with a dynamic scene, how do we update these memories? So we see that in these examples, on the left, we show the camera trajectory. So the camera trajectory is moving around in the scene, but with our method, even if the camera moves back to the original point, to somewhere that it has already generated, still the model is able to generate the previous scene instead of generating something completely new. For the memory mechanism, another thing I would like to mention is that currently there are two lines of research in memory. One line is trying to use explicit 3D reconstruction as memory, and another line is trying to use latent information instead of explicit 3D reconstruction. So traditionally, we think that 3D reconstruction provides more accurate and more explainability as a memory. But this work actually proves that with appropriate memory retrieval mechanisms, even without reconstructing this 3D scene, the model itself, the video generation model itself, also has the prior knowledge to extract accurate 3D information. Yeah, so these are works on trying to achieve interactive video generation with memory mechanism. And in the next, I will going to talk about our multimodal models and autoregressive models as for visual generation. So for multimodality, it has been a very hot topic in the past 2 years, and a traditional paradigm would be like this. So we use a language model, a multimodal language model, to predict the semantic features of the semantic visual features, and then we use a diffusion model, a diffusion decoder, to generate the image. And in this pipeline, we can unify the image generation and image understanding within this single framework. However, we found that actually, despite unifying these two tasks from the architecture perspective, it is very difficult to unify different generation tasks in the same framework. Because if we look at the different generative tasks, we found that actually they are fundamentally different. For example, if we talk about text-to-image generation, it requires a large diversity, so it requires a very rough control over the final output, and the diffusion model have to generate a lot of details to have high diversity in the results. But on the other hand, if we consider image editing, we found that this task requires very high controllability, and the diversity is not a very important thing. So, if we draw the diversity controllability trade-off on this axis, we found that different tasks are located at different points. And because of this diversity controllability trade-off, we found that it is very difficult to have a unified feature space for all of these diverse tasks. For example, in the traditional framework, there's a feature space passing from the multimodal large language model to the diffusion model. But this feature space, if we choose a very fine-grained feature, then it is beneficial to image editing because it has high controllability on what we are going to generate, but it doesn't help with diverse text-to-image generation. And on the other hand, if we select very semantic and high-level features on the, for these features, it will achieve very good results in text-to-image generation, while the image editing will suffer a lot. We explored to have a hierarchical structure for the features. So given the clip encoder, we can have a hierarchy of fine-grained features to the coarse features. And then for the multimodal generative model, we generate the features from the coarse-grained feature to the fine-grained feature. And then the diffusion decoder can select which level of feature we like for the generation task. And in this way, we can not only unify generation and understanding, but also we can unify the different generation tasks like diverse text-to-image generation, image editing, and conditional image generation. Beyond this work, something that we are still thinking about is we are always talking about unified models to unify the visual understanding and the visual generation. But what's the point of unifying these different tasks? So current models mostly treat them as independent tasks and just implement these two tasks in a unified framework. But they didn't show how this unification will help with the individual tasks, like whether understanding will help generation and whether generation will reversely help understanding. So intuitively, we think that it is easy to understand that understanding a visual understanding model, which has the strong understanding, reasoning, and planning abilities, can help visual generation because we need a lot of layout planning and reasoning on the prompts when we generate an image. And only when we can understand the prompt well and plan the layout well, we can generate the image. So motivated by this, we propose the generation chain of thought approach for visual generation with a multimodal model. So in this chain of thought design, given the user prompt like a text prompt or an image and text prompt, we first ask the model to generate the reasoning process, like the layout of the image and the attribute and object in this image. So the model reasons all of this information with a chain of thought approach, and then based on the reasoning chain, we can then generate the visual image. And all of this is implemented in a unified multimodal framework. So in order to train this chain of thought ability for visual generation, we propose a 9 million dataset with the prompt, image, and the reasoning process all annotated. And this dataset can be used as the supervised fine-tuning dataset for generation chain of thought. And further, in a recent work, we further explore that after the supervised fine-tuning, we can further use RL to boost the reasoning capability of this chain of thought reasoning. So basically, after the supervised fine-tuning, we remove all of the reasoning information in our data, and we just use the output. We just use a reward on the output, on the visual output, and use this to boost, to guide the model to find a better reasoning chain. And we found that without RL, the model is only able to fit all of the reasoning chains designed with humans by a template. But with RL, the model is able to jump out of this template and explore new strategies to reason. Yeah, so we have talked about the interactive video generation and the multimodal generation. And in the last part, I'm going to talk about some new paradigm and new architectures for visual generation. So previously, we are very familiar with diffusion models for visual generation. So diffusion models basically decompose the trajectory of noise to image into multiple steps. And at each step, we just remove a little bit of noise from the current noisy image. And step by step, we gradually obtain the clean image. Another way of generation inspired by the large language models is autoregressive models. So in autoregressive models, we are decomposing the distribution, we are decomposing the joint distribution into the marginal distributions. So basically, we first predict the first token, and then conditioned on the first token, we predict the second token. And the condition on the previously generated tokens, we predict the next token. So this is also called next token prediction in language models. So in visual generation, autoregressive model is typically designed like this. So in the first stage, we use a tokenizer to tokenize the images into discrete token space. So each image is translated into a sequence of discrete tokens. And then in the second stage, we use an autoregressive transformer to generate these tokens one by one. So we think autoregressive visual generation has several advantages. Firstly, it is easy to integrate with LMs. And because of this, it will be a unified architecture for native multimodal modeling. And lastly, it natively supports interleaved image text generation, streaming video generation, and interactive generation. So this is why we think it is a promising approach for future world models. But current technology also has some limitations. So currently, the speed and the performance of autoregressive models are still not as good as diffusion models. And this is why we see that for most commercial cases, the commercial text-to-image generation and text-to-video generation models are mostly diffusion-based. So in order to address this speed and performance bottleneck, we further look into the architecture and found where this bottleneck comes from. So firstly, we think the performance bottleneck mainly comes from this tokenizer, because in diffusion models, the tokenizer can tokenize the image into a continuous space. But in autoregressive models, we use a discrete space, and this discrete space causes a lot of information loss during the tokenization stage. And secondly, if we trace the efficiency problem, this is mainly due to the token by token strategy for autoregressive transformer. So imagine that if we have hundreds of tokens in the image, then it requires hundreds of steps in the autoregressive transformer. So although diffusion model initially also require 1,000 steps, but nowadays the acceleration approach for diffusion model is very mature, and we can accelerate it to 10 steps and even fewer steps. But for autoregressive model, we still need hundreds of steps. So in order to address these two bottlenecks, we have a series of exploration on this. So firstly, for the efficiency bottleneck, so the basic principle is that we can parallelize some prediction of tokens. So instead of predicting one token at a time, we can predict multiple tokens at a time. So based on this principle, we have this SJD, the speculative Jacobi decoding, which is a training-free approach that can accelerate an off-the-shelf autoregressive generation model by 2 or 3 times. And also, we have a training-based approach for parallel prediction, which can accelerate by up to 10 times. And for the performance bottleneck, firstly, we try to scale up the tokenizer, but we found that it is not easy. And it needs some special designs and some strategies in order to scale up a discrete tokenizer. And secondly, we are also thinking about how do we achieve a continuous level performance with a discrete tokenizer. So this is our work token bridge. So we are trying to bridge the continuous and discrete tokenizer. Yeah, so in today's talk, I will mainly talk about 2 of these works. So the first one is the parallel prediction. So a most straightforward thought for parallel prediction will be like this. So we just group the same color as a group and then predict 4 tokens at a time. But then as some initial experiments, we found that this is not ideal because it will cause a lot of local inconsistency artifacts and it will cause many artifacts in the generated images. Further analyzing this model, we found that in a discrete autoregressive model, the last step of predicting a token is always sampling from a distribution. And this sampling, if we predict multiple tokens in parallel, although we can have attention mechanisms when we inside the transformer, but in the last stage of sampling, it is always independent sampling from the distribution. So this independent sampling can cause to very high inconsistency between the nearby tokens. And in images, we know that adjacent nearby tokens are always highly correlated. And this is why we think nearby tokens should not be sampled independently. And they should be sampled and they should not be sampled independently means that they cannot be predicted in parallel. So we designed the second approach where we just we predict the very far away tokens in parallel. So in this image, we see that the same color are predicted in parallel, but they are very far away. So in this way, we can guarantee that when we do independent sampling, they have minimal influence on the final structure of this image. Yeah, so this is how we generate the tokens in an image. So on the left, we show the traditional generation approach for autoregressive models. And on the right, we show our parallelized autoregressive generation. So for the first 4 tokens, we still predict one by one because they decide the overall global and the semantics of the image. But starting from the 5th iteration, we can predict multiple tokens at a time. And in principle, we can achieve around 4 times acceleration if we predict 4 tokens in parallel. So our framework is still an autoregressive model with minimal change on the architecture itself. We just need to input 4 tokens and output 4 tokens at each step. And further, we can also output 16 tokens in parallel. So if we output 4 tokens in parallel, we can achieve 3.6 speed up. And if we predict 16 tokens in parallel, we can achieve 9.5 speed up with minimal influence on the quality of generated images. Yeah. And finally, we talk about the performance bottleneck, which is bottlenecked by the discrete tokenizer. It's not like a block decode. Inside each block is parallel prediction, and outside and between different block is next block. Yeah, it's like next block prediction. Yeah. So let's come back to. Oh, okay. Yes. Yeah. So. Yeah, that's a great question. So because inside each block, so firstly we have attention between these tokens inside this block, so they can get each other's features. And secondly, the final sampling is independent inside each block. So this requires us to design a decoding mechanism like this. So sorry, it's difficult to move back. But but basically we are not decoding the nearby tokens at the same time, but we decode faraway tokens at the same time. So these faraway tokens have typically have very low correlation. So this is why they can be predicted in parallel. Yeah, so let's go back to the token problem for the discrete tokenizer. So we have two types of tokenizer for visual generation. The discrete tokenizer can be directly modeled by the categorical modeling, like the cross entropy loss. So in this sense, it is very easy to model. And also it is easy to integrate with the autoregressive models. But on the other hand, we found a lot of training problem for the discrete tokenizer, and we cannot easily scale the vocabulary size, and the limited vocabulary size of the tokenizer can lead to limited performance in reconstruction and generation. And on the other hand, we have continuous tokenizers. So they have very good reconstruction quality. And this tokenizer itself is easy to train. So continuous tokenizer is very mature in diffusion models. But on the other hand, if we use continuous tokenizer with an autoregressive model, this will require additional modules to do the sampling. Because for discrete tokenizers with cross entropy loss, it's very easy to sample. But for the continuous tokenizer, if we still use the autoregressive model, then we will need either a diffusion head or a Gaussian mixture to sample from the distribution. And adding this diffusion head or Gaussian mixture is difficult to train stably for an autoregressive model. So in this work, we investigate how to preserve the strong representation capacity of the continuous tokens, and at the same time maintaining the modeling simplicity of discrete tokens. So our approach is that we want to decouple the discretization from the tokenizer training. So in previous approach on the left, we show that in, for example, VQ tokenizer, the discretization and the tokenizer is trained together jointly. And the middle one shows using an additional diffusion head to model the continuous tokens. And the right one shows our approach. So our approach is built upon a continuous tokenizer, but we further discretize this tokenizer into discrete tokens with a post-training quantization approach. And in this way, we can get a very large vocabulary after the quantization. And also, these discrete tokens can achieve very similar performance compared to the continuous tokens. So here we show the continuous tokenizer here, and we use a post-training quantization. We just quantize each number trained from the continuous tokenizer. So for example, if it follows a Gaussian distribution, we just quantize this Gaussian distribution with a certain approach. And because we can define the granularity of quantization and the vocabulary of this quantization, so in principle, we can have very fine-grained granularity for quantization, and we can minimize the information loss during the quantization. But one problem arises from this quantization is that we have to deal with a very large vocabulary for autoregressive modeling. And to tackle this, we design a lightweight autoregressive hat to predict the tokens channel by channel in order to decompose a large vocabulary into small vocabularies that cross-entropy loss can model. So our approach with the post-training quantization can achieve similar performance with the continuous tokenizer. And on generation, we also prove that we can achieve approximately the continuous version performance. Yeah, so that's all for today's talk. So we start from the multimodal and the interactive visual generation, and we hope this will constitute the basic capabilities for the future world models. And still, we see that in this blueprint figure, there's a lot of areas that we haven't explored. I think these are remaining to be explored by you in the future. Thank you.
Any questions?
I'm sorry, I had a quick question regarding when you were talking about parallel prediction of tokens to improve efficiency. You used the term like you try to predict far away tokens, right? I just wanted to know like what exactly does far away mean, like in terms of like, is it like token 1, token 9, like the distance, or like what each token constitutes of in terms of
information? Oh, I see. You mean how to
like what is far away in that sense?
Like how do we get these tokens, right?
Yeah.
What these tokens represent. So basically, these tokens are extracted by the encoder, by an autoencoder. So you are compressing this image into a latent space, and then in this latent space, you discretize these features into tokens. So each token can be considered as a local patch from the image with context information. Yeah, so this token still has a spatial relationship. Like if this token is on the left top corner on the feature map, then it corresponds to the left top corner patch from the image. It means these patches are far away on the image. Yeah.
Any other questions?
Thank you, Professor Liu, for your very comprehensive speech about your recent research. And I'm wondering why we should discretize these tokens, because I think characteristics of the image, it is continuous in nature.
Yeah.
So why we should discretize?
Yeah, so that's a good question. So why do we need discrete tokens? The thing is that the computation is naturally discrete. And also, if we want to apply this AR model, autoregressive model, like if we just predict the continuous features, then we still need some, So in autoregressive models, if we just predict these continuous features, then we still need something to sample because a generative model needs to sample from a distribution. It's not just predicting a deterministic feature. So we still need to sample from these continuous features. So in order to sample, there are different ways. So you can use diffusion to sample. You can use certain distribution. For example, you can assume it is a Gaussian mixture distribution, and then you can sample from the distribution. The discrete version assumes that it follows a categorical distribution so that we can use a cross entropy loss to train, and then we can just sample from this categorical distribution. And why we prefer this discrete version is because cross entropy loss is proven to be very efficient and effective for modeling the distribution. And if we use a lightweight, for example, a lightweight diffusion hat, that's also okay to sample, but it will cost extra computation, or it is not very elegant to train the model, and it will cause the instability in training.
Oh, we have a question from the Zoom meeting. How do you supervise the retrieval? Do you have ground truth for the camera viewpoints overlap?
Oh, yeah, that's a good question. Yeah, so for the context sense memory, we just use a predefined rule for retrieval. So we do not need any training for the retrieval module. But of course, if we talk about the future work, I still think that this type of rule-based retrieval is not perfect, and we still need some way to train a retrieval to train a memory module, and then extract have some way to extract or retrieve the information from the memory.
Any other questions? And I have a question regarding the second where you introduced the context as memory.
Yeah.
Do you need to predict the camera pose from the video?
Oh yeah, in that work we just assume the camera pose is given. So because the user when the user interact with the video, the user has the action given to the model, and from the user action we can
It's like
get
the user
the
draw some
camera
line to
trajectory.
draw the trajectory of the camera pose.
Oh, sorry.
Draw the trajectory of the camera movements, right?
Yeah.
Oh, okay. But during the training, how to extract these camera motions?
We just use data with camera motions. Yeah.
Oh.
The simulation data.
Please.
In the context as memory, this work, we should catch all the previous image as memory and then select the contact. Is that right?
Yes.
Oh, okay.
More questions?
Professor Liu, I'm still a bit uncertain on the discretizing in the autoregressive model. I'm not understanding too much about that part.
So why do we need to discretize, right?
Yeah.
Yeah, because the reason why we need to discretize is that, so firstly, we are talking about generative model. So generative model needs to model the overall data distribution, and then in order to generate one sample from this distribution, we need to sample from the so generative model need to sample from the distribution, right? Because we model a distribution, and then we need to have some way to sample from it in order to generate a certain image or video. And so if we use continuous features, then we need to have some way to sample from these continuous features. For example, we can assume that these features characterize a Gaussian mixture distribution, and then we can sample from this Gaussian mixture distribution. Or we can use a diffusion model to do the sampling. So diffusion model is also designed to sample. But on the other hand, if we do not want this extra hash or extra computation, then we need to have a certain distribution that can be described with the features. And one way is that we can just define a categorical distribution. And if we so with a categorical distribution, we can easily sample. But the problem is that if we define a categorical distribution, then we need the data to be to fall in this limited vocabulary distribution. So the data cannot be continuous data. So it has to be the data belonging to a certain vocabulary or a certain number of categories so that we can train this model with the categorical distribution.
So does it mean we sort of like split the, how can I say, split the generation into different category, and for different category, they have some continuous latence?
Yeah. So we are basically, so each image token, we assume it falls into one category. So an image can be translated to a sequence of discrete tokens, and each token has a category number.
So does it mean that it has like many categories for each feature vector? Like
yes,
each dimension is a class of category or something like that?
Or you can understand it as each feature vector belongs to a certain category. So we can cluster on the continuous feature space into different categories.
Oh, okay, I see, thank you.
Okay, let's thank the speaker again.
Thank you.
Thank you.